My name is Vivas. I am an associate professor at the math department at Ohio State University. I've been at Ohio State since 2014. I completed my PhD at University of Michigan, and after that I did postdocs at Purdue University, Brazil, and France before coming to Ohio State. I'm originally from Peru. When I was younger, I definitely was very interested in mathematics. I love puzzles, problems, but I also like other things. I guess I wasn't very familiar with the academic circle in general. My parents are not academics, and in Peru at the time, it was not very common to have an academic life. So I was not aware that mathematics could be a career. In fact, I thought people who did mathematics then ended up going to be high school teachers in mathematics. That was the most common career path in Peru. But yeah, I found out along the way that it was possible to do research in mathematics throughout, and that sounded really appealing and really fun. I actually started my undergrad in engineering. So I did engineering first, which had a lot of math classes, which I loved, and that's what I chose engineering. And so that's when I realized that I only liked math classes. I decided, okay, maybe I should pursue a master's first. I like the excitement of discovering things. I like very much the precision of mathematics. It's not, having said that, it's not a very precise science in many ways, but once things are cleaned up, it looks very nice and neat and easy to follow in some ways. Say you are trying to uncover some kind of hidden structure between two different things, and you kind of can see that it's there, but it's not clear how they are really similar or what kind of connection there is there. So in that respect, I mean, it's not very precise until one makes it even more precise. I will say it is like a process of discovering things in mathematics. So I guess first one has to learn definitions and what math people are working on. That takes a long time, and that's sometimes like a very big barrier to understand what's next. Having said that, like I think that a lot of what math research is about, it's really about playing with concepts and definitions and looking for connections or trying to solve a problem. I think there is a lot of research as people think it is like going to a library, open a book, finding out some bibliography that can be helpful. It is in some ways similar to that, but instead of going into a library and opening books, well, sometimes you're looking at other papers, sometimes you're thinking about in your own head, what could it be, this connection from this thing with another or this answer.
In the next section, Dr. Vivas talks about functions. You might remember about functions from high school. A function is a relation between two sets of objects. In the scenario Dr. Vivas refers to, these objects are numbers and the function is given by a formula. For example, here the function f of x equals 2x plus 1 relates every number x with the result of multiplying that number times 2 and then adding 1. Thus, f of 1 is 3, f of negative 2 is negative 3, and f of 3.14 is 7.28. A function can also be represented by its graph. Here you are seeing the graph of our previous example, f of x equals 2x plus 1. In school, we focus on nice functions, but functions can be very weird too. Mathematically, we study certain characteristics of functions that make them quote-unquote nice. For example, roughly speaking, a continuous function is one where the graph doesn't have any gaps. A differentiable function is one that doesn't have any pointy peaks.
When one thinks of functions, there are functions that are very complicated and very weird and non-continuous. But then if one starts asking for a little more of your function, you can ask for functions that are differentiable, that they have derivatives everywhere, etc. And one very nice class of functions are analytic or holomorphic functions. These include all functions that maybe you have thought of, like all polynomials or sine and cosine. All these functions are analytic, exponential. And these functions have really nice properties. And it turns out that it makes a lot of sense to define them not into real numbers, but into complex numbers, which is an extension of the reals. And in this way to extend these functions to all these complex functions, to all the complex numbers, one finds very nice structure for these functions and lots of very nice behavior. And so all this field is called complex analysis, because one basically analyzes the functions that are defined as complex functions or analytic functions or holomorphic functions. There is many different fields that study these analytic functions, and complex analysis being basically the umbrella of all of them. And under this umbrella, there is different subfields. I work in several complex variables, which means that instead of my functions being defined in one complex variable, they are defining several complex variables. So instead of being defined on C, they might be defined on C cross C or C cross C cross C. So depends on higher dimensions of C, basically. There is different ways to explain dynamics. In some ways, we are thinking about the same thing all the time, which is things that are changing throughout. Say, for instance, the weather. How is it changing? If one wants to keep track of the temperature, we can keep track of the temperature every day. So an analytic function, a complex analytic function, you can think of it as a function going from space to another space, C to C. And we are just going to study what happens if I take one point and I apply this function to this point. And then I apply the function to this output. And then I apply this function to the new output of this and see where this point is going. This is what we call an orbit of a point. So let me say, for instance, an example, like if I just think about the square function, I start with 0 and I square it, I get 0, and I square that number and I get 0. That will be an orbit. Or if I start with 1, I also get 1 again and 1 again. But I can start with other numbers, like 0.5, and we can square it and we're going to get 0.25, and we square it again and we're going to get, I don't know, 0.0625 maybe, or something like that. And so you see that the orbit is changing, and in fact it is approaching 0. So these are the kind of questions that we ask. For which, given a function, what can we say about its orbit? Or other ways is, given this family of functions, what do they all have in common about orbits and things like this. A complex number, it's basically an extension of the reals, and as I said, it's mainly because we want to solve every equation. So we know how to solve 5x plus 7 equal 10. We pass 7 to the other side and divide by 5 when we get an x. But say we want to solve x squared plus 1 equals 0. We do not have a solution on the reals to solve this problem. We will have to get x squared equal minus 1, x equals square root of minus 1. And this is not a real number. There is no real number whose square added 1 gives us 0. So we construct a new number called I, which is the complex number. And then basically it's kind of amazing and a miracle that just using this I new number, every solution of an algebraic equation has, every algebraic equation has solutions in the complex number, in the complex field, yeah. So this is known as the fundamental theorem of algebra, and it's extremely powerful and allows us to do dynamics in the complex plane. So now, say I'm going to study again the function f of x equals x squared. Before I couldn't say this point is going to give me minus 1, because there wasn't a real point that gives me x squared equals minus 1. But if I extend it to all of C, I do have a pre-image of minus 1. I will go to minus 1, and actually negative I also will go to minus 1. So extending it in this way allows me to think about pre-images of every point. I don't have to say like only the positive numbers are going to have pre-images. And by a pre-image, I mean the number that it's coming from, a number whose function gives me that specific number. So that's the advantage of studying with complex numbers. And once we extend these to complex numbers, we see already very rich structures in quadratic polynomials, for instance. This is very related to the well-known Mandelbrot set. And already there's rich theory, open problems, things still not worked out completely for this. Only, for instance, the quadratic polynomials, cubic and quartic, all of these becomes even more complicated. And so sometimes people study instead other aspects of complex dynamics. Say for all functions that are polynomials, there's other aspects of complex dynamics for exponential functions that are not polynomials at all, and so forth. So yeah, different people study different functions. By that I meant just basically any polynomial equation. So say x or x squared or x cubed, and you can combine these little basically powers to make any polynomial you want. Something like 2 plus 5x plus 7x squared plus 10x fourth minus I times x to the fifth. This is a polynomial equation. And it turns out that polynomial equations have as many solutions. Polynomial equals 0 have exactly the number of degree solutions. So for this example was exactly 5 solutions on the complex numbers. But on the reals, sometimes you have none. F is analytic if it has a complex derivative. And I think that we're very familiar with the study of derivatives by itself, sometimes as a limit of two differences, and it's the same here, same thing here. I want that at any point, if I move a little bit outside my point z, and I subtract this function, that this has a limit when w goes towards z. So if this exists for every point, that means that this is an analytic function. So this is very different with respect to real analysis, because in real analysis, when you have derivatives at each point, sure, there will be a differential function, but maybe the second derivative will not exist. Whereas if you work in the complex numbers, the fact that these numbers are on C, you're basically dividing a whole complex number by another whole complex number. And that is kind of dividing vectors, which is kind of hard or impossible, basically, as long as you're in, say, R3. But in C, you're in the variables 1 and I, basically, you can do this kind of division, and this exists for all C. This is what it means to be an analytic function. Okay, so F is analytic if this. And this immediately gives you that all the derivatives exist. Gives that, like, any derivative you want exists. So it is very powerful, even though the condition is exactly the same that in real analysis. The fact that these are vectors gives you so much more power that allows you even to have higher derivatives exist. Yeah, choosing a problem to work on, that's something that I still I'm learning about. In general, for me, it has been mainly really things that I find fascinating and I want to understand what's happening. Also, things that my co-authors sometimes find fascinating, like we work together to see. I think the most interesting problems to me are the ones that relate different parts of mathematics. If I'm thinking about some analytic problem and it has some geometrical interpretation, I find that very interesting and trying to uncover and understand exactly why there's a connection. It's very nice. Things in which maybe open questions that I think are fundamental and that can help out for other problems are things also that I find very nice to work on. And for my PhD thesis, I remember my advisor was pretty keen on me solving a specific problem, which I still haven't solved, actually. It's still an open question, by trying to solve this problem, I uncovered a different type of phenomenon that I didn't know about, and that it had its own life in some ways that was separate of this problem. So it was really like trying one thing and then during the way they're discovering a different one that I worked on for my thesis. Yes, after that, I will say many questions that have motivated me are related between this difference between what happens in one complex variable and several complex variables. So the theory is very rich and beautiful in one complex variable, and it's harder and not as well understood in several complex variables. So sometimes some theorems, I think, that are fundamental in one complex variables do not have a counterpart on several complex variables. And I am interested in finding those counterparts, finding the questions, or even finding the counterexamples, things that will not happen on several complex variables. An open question is, in general, a question that many people have asked about and they have not yet have an answer for. In complex dynamics, I think there is a central question, which is the Mandelbrot local connectedness question, conjecture, actually, known as MLC from its initials, conjecture. And that, for instance, has something to do with a topological property of the boundary of the Mandelbrot set. The Mandelbrot set being a fractal picture that emerges when one studies quadratic polynomials. This fractalish picture that has beautiful visualizations that one can find online, or you can just find it even on books. It's very well studied, but even there we still don't know if this set is locally connected or not. So this is an open question, a very famous open question. Let's just think about the injective functions from C to C and the surjective functions, meaning that every value is going to come from some point, and no two different points go to the same value. One can actually understand exactly how many of these functions are. It's basically just a linear function. F of z has to be a linear function. It has to be a constant times z plus another value, like a linear function in real variables, like 3x plus 5 or something like that. There's no other one. Whereas if we go to C2, there are so many more, because the second variables, f of x comma y equal some two variables, gives us so much freedom and so much space to have many other functions besides the linear functions that are going to be injective. So we will have much larger class of families that are injective and surjective. So if one thinks about, for instance, the dynamics on the study of injective and surjective functions on C, is much simpler or much better understood than studying the same dynamics of these on C2.
Let's look a little closer at the problem that Dr. Vivas just described. She's talking about injective and surjective functions. Before, we said that a function relates two sets of things. It takes things from one set as input and assigns each a single thing on the other set as output. Something like this is not a function, because when we input 2, there are two possible outputs. For f to be a function, f of 2 must be a unique result. Injective and surjective functions have additional conditions on top of the basic function condition I just mentioned. In an injective function, the output never repeats. Once you've assigned an output, you cannot use it again and assign it to another input. On the other hand, in a surjective function, there cannot be any unused elements on the output set. A function that is both injective and surjective is called bijective. Bijective functions are like trying to break the class into pairs. Every element on both sides has a unique partner. For bijective functions from R to R, the graph looks like it crosses the whole Cartesian plane. Dr. Vivas explained that mathematicians have discovered that for a function from C to C to be bijective, it has to have a formula like f of c equals a times c plus b. You can change A and B to be any complex number, but every bijective function from C to C will have such a formula. There are no bijective functions of other types of formulas. However, when we look at functions from C2 to C2, which remember have two complex numbers as input and two as output, then mathematicians have not yet figured out all the possible formulas for bijective functions. What Dr. Vivas is saying is that mathematicians know functions from C to C very well, but the same problems they have solved there are still being studied for functions in several complex variables.
So one type of problem that I have been interested on is understanding or extending a theorem in one complex dimension. So this is one complex. So these functions go from C to C. And the type of functions that we have are functions that start being almost the function itself, but then I perturb with a higher degree term. Say something like this. And so there is a theorem actually of the 1920s. These are two French mathematicians that explain that for any map of this type, the behavior of what happened to the orbits at zero is completely well understood by just looking at the next term that is not the identity term. So in this case, I'll look at this one. You look at the smaller of all of those, in this case is 2, and so they explain that you will have 2 petals. Let me draw them this way. And on these petals, every point, the orbit of every point is going towards 0. Every point that I take on this complex plane will map towards 0. And 2 repelling petals, which the opposite happens. At every point from here is actually coming from somewhere outside. So this is called as the flower theorem because of the petal terminology. What's happening at this intersection? Well, they are going out first because yellow tells me they should go out, and then they come in by the browner. The question is, what is this in 2 dimensions? And by that I mean, say, a function from C2 to C2. So how can we think of a function from C2 to C2? If you just think about it as 2 variables, which each one is a complex number. And the same idea, what happens if I have C, W, and then I perturb by something. Say I perturb by C squared plus W cubed, C cubed minus W squared, or something like that. What is the petal theorem in this context? And this is still something that we don't understand completely in many, many cases. Many functions on this respect do have some kind of flower theorem or not. So I'm interested in these kind of questions for this for this theorem, to extend this theorem. So if I would have, for instance, 100 here, it's still the same degree, right? This is still telling me the same thing. So what is going to change in the picture is that this might be a little smaller. If I had changed it here to I or something like that, I might be rotating my petals. My petals might be in a different direction. If I would have changed here to, again, something similar, I could have changed in the next one to 7. My petals will have a different shape somehow. Say C plus Z to the 4th. So then you're going to have, it's this number again that tells us. So before it was 2, and so that means one take 1 less than that. So this is 4 minus 1, so it's 3. So there should be 3 kind of attracting petals, and then 3 repelling petals. Oops, this should enter. And this brown picture should have. So that will be for this case. You always look at this number and you take one less, and that is going to tell you how many attracting, in this case these brown ones, and how many repelling, in this case these ones over here.
As we said before, complex numbers are not on the number line. Instead, they can be represented on a Cartesian plane. We write the real component as the horizontal coordinate and the imaginary component as the vertical coordinate. For example, the complex number 2 plus I corresponds to the point 2, 1, while 3 minus 3i corresponds to 3, negative 3, and 4i minus 1 is negative 1, 4. The flower theorem works for polynomial-like functions that take a complex number as input and give another complex number as output. The function must include a linear term, the variable itself with no exponent. The function can include more terms with higher exponents. Once you have your function, you have to look at the next smallest exponent. Whatever that number is, the orbit of the function will have one less petal than that of each type. There are 2 types of petals, attracting petals and repelling petals. Say you take a point inside one of the petals. Remember that this point is a complex number. You then plug it into the function. Whatever the result is, you plug it into the function again. You get a result and plug it into the function one more time. You repeat this process over and over. What the flower theorem explains is that if the point you started with was in one of the attracting petals, then after repeating the process over and over, you will eventually get to 0. On the other hand, the points on the repelling petals, after plugging them into the function over and over, will eventually end outside the petals where they started. The shape, position, and size of the petals changes depending on the specific function. What Dr. Vivas is investigating is how this flower theorem changes when the function is a multivariable function, meaning that instead of taking as input a single complex number, it takes 2 or more, and it also outputs the same amount of complex numbers. As in this example of a function from C2 to C2, which takes 2 complex numbers as input and returns 2 complex numbers. Notice that there's a formula for each output, but both formulas include the input values plus something else, as the flower theorem requires. The problem Dr. Vivas and other mathematicians are trying to solve is if these multivariable functions also present attracting and repelling petals or not, or perhaps in some cases they do, but in others they don't.
Suppose F is analytic and injective. Then it turns out, well, maybe just analytic, sorry. Analytic. Then it turns out that C minus F of C cannot contain more than 2 points. But in 2 complex variables, if you take a function f from C2 to C2, so this one can think of as like this is C, this is C, and if I take a function from here to here, unless it's a point, that's one case. If it's not a point, it has to cover everything, and maybe I will avoid 1 point or another point at most. So in this case, I actually, the similar statement, the similar theorem will be F analytic. I'm going to impose a little more because non-constant will mean like different things here, since I could have a constant in the first variable and non-constant in the second variable. So let's say I impose that it's injective. So we know that the image of this the complement of this image, basically everything that is not here, can contain one line. Now the analog of like points will be lines, right? And cannot contain three lines. These are none.
Three or two?
Three,
Huh.
and two it's not understood. So this is actually what I was working on in my thesis. That is still not known. Like, is it possible that it cannot contain two lines, or it cannot?
This other problem that Dr. Vivas discusses deals with the image of a function. The image of a function is the collection of output values it produces. For example, the image of the function f of x equals 1 is 1, because 1 is its only possible output. No matter what value you feed to it, 1 will be the output. On the other hand, the image of the function f of x equals 2x plus 1 are the reals, the whole number line. It hits every single value on the number line. However, if we look at these same functions but only use the naturals as input, then the image is the odd number. We will never hit an even number. This notation that Dr. Vivas uses represents the values that the function doesn't hit, that will never occur as output. In the problem Dr. Vivas describes, she is looking at the image of analytic functions from C to C. In this picture, recall that the complex numbers can be represented as points on the Cartesian plane. If you apply f to every complex number, then you will get as output almost every complex number, possibly skipping only one or at most two numbers, but nothing more. This is true as long as the function is analytic and non-constant. Constant functions only hit one value because they give the same output for every possible input. As before, Dr. Vivas is studying how this property changes for multivariable functions.
I like biking a lot. I'm not a serious biker. I bike school from my home. I like activities, being outdoors, being outside. I like hiking and biking. I have two little kids, so it's harder sometimes to bike and hike with them. And besides that, I enjoy reading a lot and knitting and crocheting during the winter time. That's my outlet.